Today I'd like to talk to you about what we learned in our photoelectric lab that we did the other day. Okay, I'd like you to start out by drawing the setup that we used in lab, which is a modified version of the photoelectric effect. So it starts with a lamp, but a lamp where we can control the color or wavelength, and we can control the brightness. The lamp is positioned such that the light shines through a hole in a metal plate. This metal plate will be called our collector. This metal plate will be connected to the negative terminal of a power supply. We're not going to be using the power supply quite yet, but that's where we'd like to have it hooked up to. That light again shines through a hole in the plate and it hits our target metal, which we're going to start with potassium. That target metal is connected, I know it got cut off here, to the positive terminal of our power supply. All right, so this is our setup. Now, we shine light onto the potassium. When the light hits the potassium, electrons are ejected from the potassium. That is what is known as the photoelectric effect. Photo, that is light, hits the metal, knocks electrons off. Photoelectric effect. Thing to realize is it doesn't always happen, and we're going to be learning today what factors about the metal and the light determine if electrons are knocked off, how many electrons are knocked off, and the energy of the electrons that are knocked off. But the first thing you want to make sure you write down is that it's possible for light to knock electrons off of a metal. We can draw it out looking like this. So we have light hitting the metal and electrons popping off with a certain amount of energy. We're going to be using the power supply in a little bit to figure out that energy of the electrons. Okay, so here's our first thing we're going to do. We're going to shine the light. We see electrons coming off. We're going to increase the wavelength of the light. Electrons still come off. We up the wavelength again, 530, electrons still come off. But at 540, you'll notice the light is shining on the metal and no electrons are coming off of the metal. How do scientists know if electrons are coming off the metal or not? Well, one thing we could do is have a current meter, an amp meter, connected into our circuit, and when the current reads 0, we know there is no flow of electrons through our circuit. So anyway, what we learned is that there is some place in this spectrum where on one side, electrons are knocked off of the metal, and on the other side, they're not. This spot, this magic color, this magic wavelength is called your threshold frequency, threshold wavelength, or threshold color. Okay, and for potassium, this threshold seemed to lie somewhere between 530 nanometers and 540 nanometers. All the colors on this side, which would have smaller wavelengths or larger frequencies, can knock the electrons off. All of these electrons are knocked off. Anytime you have a higher wavelength or a lower frequency, the electrons are not knocked off. Okay, so again, threshold frequency, threshold wavelength, threshold color. Second major idea is that there is a threshold color, and any one that has a frequency lower than that or a wavelength higher than that cannot knock the electrons off. We're going to switch to a different metal. We're going to use cesium. Again, we're going to start in the 500s. 530 knocks it off. 540 knocks it off. 550, they still get knocked off. 550, 560, 570, they're still knocking the electrons off. 580, they're still coming off. And somewhere between 580 and 590, we're now moved a little bit further along in our spectrum. Our threshold is now over here. So our next key idea is that the type of metal determines the threshold frequency, or wavelength, or color. It just so happens with cesium that it's easier to knock the electrons off. A lot more colors are able to knock the electrons off than they were with potassium. Okay, next we'd like to look at the electrons again hitting the light again hitting cesium, the electrons coming off. We're going to make our light way down here on the purple end of the spectrum. And what we want to find is how much energy these electrons have. So you'll notice what we did is we changed the voltage. That is, we put negative charges from the negative terminal onto this plate. That negative plate repelled the electrons, and when we had enough voltage, we were able to stop the electrons. This is called the stopping voltage. For this wavelength and this material, the stopping voltage seemed to be somewhere between 0.5 and 0.6 volts. Okay, stopping voltage. Scientists use that stopping voltage to determine the kinetic energy of the electrons when they're ejected from the cesium. So this is the charge of the electron, and that is the voltage that it took to stop it. Okay? Remember, how do we know when the electrons stop? We watch the current meter, and when the current reaches 0, we know we stop the flow of electrons through the circuit. Okay, when we plot it out, we do a whole bunch of different colors, a whole bunch of different frequencies. We use the power supply to stop them. We get a graph that looks like this, a very, very important graph. We have kinetic energy of the electrons on the Y, the frequency of light on the X. You'll notice it is a linear graph that has a distinct starting point. That starting point is your threshold frequency. All of these frequencies, that is wavelengths or colors, cannot knock electrons off. All of these frequencies can knock the electrons off. And you can see that the higher the frequency, the more energy the electrons are going to get. If we were to replace it with a different material, we would get another linear graph with the same exact slope, but a different threshold frequency. As we saw before, cesium and potassium had different thresholds, but it turns out they would have the same slope. So the slope is not determined by the metal. So our equation y equals mx plus b, the y is the kinetic energy of the electron. The slope is a universal constant. It does not matter what the metal is. It turns out to be Planck's constant. The x-axis is frequency, and the y-intercept happens to occur in the negative values, so we're going to say minus some value. This is called the work function, and it is determined by the metal target. Cesium and potassium would have different work functions. Okay, so this equation is going to turn out to be really important in the birth of quantum physics, as we're going to see really, really, really soon. Okay, so let's make sure you understand how the equation relates to our picture. So we have kinetic energy refers to the electrons. The HF turns out to be the energy of the light that is coming in. And this guy is determined by the metal. So just to make up some numbers, these are not real, but just to make up some numbers, let's say the light had an energy of 5 electron volts. And let's say the metal had a work function of 3 electron volts. That means it takes 3 electron volts worth of energy to take away the electron. That would mean the electron has 2 electron volts left. I hope that makes sense. It's just conservation of energy. We started with 5, that was the light. We took away 3 to pull the electron out of the metal, which means the electron has 2 electron volts worth of energy after being ejected. Okay, I want to make sure you understand the effect of brightness. So the brightness, you'll notice, does not appear in the equation. So the brightness does not affect if the electrons come off. The brightness has no effect on the energy when they come off. But the brightness does affect the number that come off. So you'll notice I upped the brightness from like 20 all the way up to 100. It had no effect on whether or not electrons came off. However, if the electrons are coming off and I increase the brightness, I'll get more electrons. So more brightness means more electrons come off of the metal. Okay, we already said this, but just to make sure it's clear, if you use a higher frequency of light, the electrons are going to be harder to stop. That means higher frequency colors have more energy. We are now at the point where we can actually start to understand what quantum physics is all about, and that's going to happen in our next lesson. Just remember all the key ideas from the photoelectric effect, because that's what's going to trigger the birth of quantum physics. So quick summary: light hits a metal, electrons might come off. Looks like that. The wavelength or the color determines if they come off. Some wavelengths can knock electrons off, others can't. The type of metal determines what that magic wavelength is going to be. Our graph turns out to be a linear graph, and the slope is a universal constant. The y-intercept is determined by the type of metal that we use. Brightness does not affect if they come off, it affects how many come off. And they are the key ideas for the photoelectric effect. Tomorrow, or in the next lesson, we will be looking at how this triggered Einstein's brain to come up with the idea of the quantum.